Hello students, welcome to the third session of D and F block elements, and here we are going to discuss regarding F block elements. So what are F block elements? What are their general characteristics? ಇದನ್ನೆಲ್ಲ ನಾವು ಈ chapter ಅಲ್ಲಿ discuss ಮಾಡೋಣ. Last two sessions we have discussed about D block elements. Hope those concepts are quite crystal clear. Right? Okay. So let us start with F block elements. So F block elements anta andre ಏನು? So we have already discussed D block elements discuss ಮಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ why this name is D block, F block anta ನೋಡಿದೀವಿ. The name of every orbital is derived from its respective atomic orbitals, right? The name of every orbital is derived from its respective atomic orbital. Like you have S block, you have P block, you have D block, and you have F block. So, and these SPDF orbitals, they are derived from the values of what? They are derived from the values of azimuthal quantum numbers. They are derived from the values of azimuthal quantum numbers. Now, please don't ask what is azimuthal quantum number. So azimuthal quantum numbers only, you have 4 quantum numbers, out of which 3 quantum numbers are the solutions. They are the solutions of Schrödinger wave equation. That they are principal quantum number, azimuthal quantum number, magnetic quantum number, and one quantum number that is spin quantum number that is not a solution of Schrödinger wave equation. That is regarding the spin of the electron, spin angular momentum anta ಹೇಳ್ತೀವಿ. So SPDF orbitals, they are derived how? They are being derived from the values of azimuthal quantum number denoted by letter L. So L values, you all know, just a brief basics, I'll just cover it. So L values are 0, 1, 2 and 3, yes or no, and so on. So L value 0 idre ನಾವು ಅದಕ್ಕೆ S orbital ಅಂತೀವಿ. L value 1 we call it as P orbital, S value 2 we call it as D, S value 3 we call it as F, as we have studied in our lower class, that is 11 class 11 ಅಲ್ಲಿ ನಾವು ನೋಡಿದೀವಿ, right? So here you have sharp principal diffuse fundamental. SPDF stands for what? Sharp principal diffuse fundamental. So F orbital fundamental, F stands for what? Fundamental. So elements in which the last electron enters into the F orbital, the elements in which the differentiating electron, ನಾವೇನ್ ಹೇಳ್ತೀವಿ, call it as differentiating electron, or the last electron enters into the F orbital of anti-penultimate shell. Yes, anti-penultimate shell. So here anti-penultimate shell ಅಂತಂದ್ರೆ ಏನಪ್ಪಾ? Anti-penultimate shell. So S block ಅಲ್ಲಿ P block ಅಲ್ಲಿ discuss ಮಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ you have studied there. In S and P block, what happens? The last electron enters into the ultimate shell, that is the last shell. In D block, as we have discussed in our last session, we have covered it. D block ಅಂದ್ರೆ ಏನು? The last electron enters into the D orbital of the penultimate shell, ಅಂದ್ರೆ n-1th shell. It will enter into n-1th shell. Whereas in S and P block, it enters into nth shell. In F block elements, the differentiating electron enters into the F orbital of anti-penultimate shell, andre n-2th shell. Last but second shell alli electron enter ಆಗುತ್ತೆ. Therefore, we call it as anti-penultimate shell. So this is a quite brief introduction regarding S and P, F block elements. So F block elements are the elements in which the last electron enters into the F orbital of anti-penultimate shell. So here you can see the F block elements consist of two series. That is lanthanoids and actinoids. ಕೆಲವೊಂದು book ಅಲ್ಲಿ lanthanides ಅಂತ ಬರ್ದಿರುತ್ತೆ, LANTHANIDES, actinoids NACTINIDES. So you need not worry much about the spellings there. That doesn't make much difference. You take it as lanthanoids, actinoids, or lanthanides and actinoids. Okay. So lanthanides are also known as rare earth metals. Now the question is why they are known as rare earth metals? Because these 14 elements, will come to it. Lanthanides alli ಎಷ್ಟು elements ಇದೆ, actinides alli ಎಷ್ಟು elements ಇದೆ, we'll discuss that. These 14 elements of lanthanides, the 14 elements of lanthanides, they are called rare earth metals. Why? Because they are less abundant, or let me be very specific, they are least abundant. They are least abundant in the earth's crust. Therefore, we call them as rare earth metals. Fine. Then actinides, they are known as radioactive elements. ಅದು ಯಾವ ಎಲಿಮೆಂಟ್ಸ್ ನಾಟ್ ಫ್ರಮ್ ಥೋರಿಯಂ ಟು ಲಾರೆನ್ಶಿಯಂ. ಆಕ್ಟಿನೈಡ್ಸ್ ಸ್ಟಾರ್ಟ್ ಫ್ರಮ್ ಥೋರಿಯಂ ಅಪ್ ಟು ಲಾರೆನ್ಶಿಯಂ. ದೇ ಆರ್ ಕಾಲ್ಡ್ ರೇಡಿಯೋ ಆಕ್ಟಿವ್ ಎಲಿಮೆಂಟ್ಸ್. ದಟ್ ಈಸ್ ಇಂಪಾರ್ಟೆಂಟ್ ಫೆನಾಮಿನಾ That is not a simple property or anything as such. Very important phenomena of emitting the radiation their own. So radioactive elements antivi, all the actinoids are radioactive elements. We'll discuss the actinoids ಬಗ್ಗೆ ಮಾತಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ we'll go in deep about it. Okay, so let us start with let us have a little bit more study regarding F block elements, and then we will start with lanthanides. See why these are F block elements. If you see the periodic table and why these are separately placed, ನೀವು periodic table ಅಲ್ಲಿ ನೋಡಿದ್ರೆ like in a D block, when I was speaking about D block itself, I have told you all. So when we talk about periodic table, ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ, in the periodic table S block elements are placed at the left, P block are at the right, leftmost are S block and rightmost are P block, and these D block elements are in the middle, and F block elements, they are present at the bottom line. I have shown this. They are present at the bottom line. Periodic table al nodidre it's something like this, correct? So we can say they are placed away outside. Horage hakbittidivi avarna periodic table alli. Why they are placed separately? What is the speciality? Do they make any other groups or anything as such? Okay, so these are F block elements. This first series, iduk now series 1, series 2 anta heltivi. These first series are called lanthanides, and the second series are called actinoids. I am comfortable using the term lanthanides and actinoids. You can take lanthanoids and actinoids also. So because these F block elements are unique, these F block elements, they are unique, they are different, they are special and tanri. So they are placed separately. Now the question is, okay, you said me they are unique, fine. Why they are unique? What is the reason to make them unique, to show unique character? So here you can see, ನಾವು periods PU1 class 11 ಅಲ್ಲಿ ಮಾತಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ, when we are talking about periodic classification, you could see the speciality of the groups is all the elements which come in a group are similar. So in the periodic table you can see vertical similarity, right? You can see vertical similarity. This is known to you. Vertical similarity is seen. But in case of lanthanides and actinoids, you can see horizontal similarity. You can see horizontal similarity. So they are very special. They have been placed separately. Now these very important and interesting point here is, see, if you look at the periodic table, you will get to know these elements, they are formal members of group 3 only. They are formal members of group 3. What does this mean anta ನೀವು ಕೇಳಿದ್ರೆ, S block elements, there are 2 groups, group 1, group 2. P block elements, these are the groups, 6 groups are there, 6 group 13 to 18. D block elements alli group 3 to group 12 anta ಹೇಳ್ತೀವಿ ನಾವು. F block, how many groups appa? In F block, they are made up of only group 3. Now the question is, just now you said lanthanides alli 14 elements there, actinoids alli 14 elements there. So these are so many elements here. If you look at the actual periodic table, we'll get to know ishtu elements alla onde group alli hege. So here there is group 3. In this group 3, if you look 4th, 5th, 6th period alli nodidre ನೀವು, if you see here there are, one is lanthanum and another one is here actinum. Yes, only in this particular block, these all lanthanides are being placed. All these lanthanides are being placed in this particular block. So behavior is somewhat similar. So separate agi madilla adana. If you look at this these 2 periods, you'll get to know that. So let me explain you how. In these F block elements, there are 14 lanthanides and 14 actinoids, right? So lanthanides antandre, we call it as 4F series. 4F series. Because the last electron, more specific, I'll do F block elements there, but here I call it as 4F, and actinoids I call it as 5F series. Why? Because in lanthanides, the last electron enters into the 4F orbital, whereas in actinoids, the last electron enters into the 5F orbitals. The name lanthanide comes from lanthanum. Lanthanum. The name lanthanides comes from lanthanum. Symbol is LA. Periodic table open ಮಾಡ್ಕೊಂಡಿಟ್ಕೊಂಡು ನೀವು ನೋಡಬಹುದು. So LA, the name comes from this. So in the house of lanthanum, all lanthanides are being placed. They are present. So in the single block, we can't show 14 elements, right? ಇಲ್ಲೇನ್ lanthanum ಇದೆ ಅಲ್ಲ, in its house, ಇದರ ಮನೆಯಲ್ಲಿ ನೀವು 14 members ಅನ್ಬೋದು. ಇದು ಒಂದು ಮನೆಯಲ್ಲಿ 14 members ಇದಾವೆ. But see, in one block, we cannot show all the 14 elements, right? Therefore, they have been placed separately. Ashte, nothing to think much about it. Same thing, you take it for actinium. Actinium, you can look at the element actinium, AC. In its house, other manelli, actinium block all the 14 actinides are being placed. All the 14 actinides are being placed in actinium. But can you show all the 14 elements here in one single block? So to make that study simple and easy, they are being placed separately. Is that clear? So here to conclude, F block has two series. One is 4F, another one is 5F series. 4F series ಹೆಸರೇನು lanthanides, 5F series ಹೆಸರೇನು actinides. So lanthanides, you have lanthanum. This is not the member of lanthanides. Please remember it. 6s2. Then you have cerium. The first member starts from cerium. Configuration bandbittu 4f1, 5d1, 6s2. So this is the configuration of cerium. So lanthanides, general configuration bekappa. So you write it as noble gas configuration 4f 1 to 14, 5d 1 and 0 and 1. Let me write it like this, and 6s2. This is the general configuration. 14 elements yavavappa. It is from 58 lanthanum, sorry, 58 cerium to 71, 58 to 71. You can count and see there are 14 elements. So these are lanthanides. Actinides ಬಗ್ಗೆ ಮಾತಾಡಬೇಕಾ? So first here element followed by actinium are the elements 14 and they are called actinides. So first element ಬಂದ್ಬಿಟ್ಟು thorium. Actinium ದು ನಿಮ್ಮ configuration ಬೇಕಾ? So actinium you can write it as 5f0, then 6d1, 7s2. Then take the example here. You have 5f1, 6d1, 7s2. So thorium configuration like this. It is the configuration. Okay. So here you can see the differentiating electron in lanthanides or in actinides. It is entering where? It is entering into n-2 shell. This is nth shell, this is n-1th shell, this is n-2 shell. Similarly here, n-2 shell. Therefore, we say they'll enter into the anti-penultimate shell. Ultimate andre nth shell, then penultimate andre n-1th shell, and anti-penultimate means n-2 shell. So when we talk about lanthanides start from cerium to lutetium. Cerium in the hididu lutetium varagu lanthanides ide. Name is lanthanide, but there is no lanthanum. Why? The name is lanthanides. There is no lanthanum. See, look at the configuration of lanthanum. I have written here. It is 5d1, 6s2. There is no 4f orbital or 4f orbital illa. Yes or no? So we say that F block elements and there should be 4f orbital. Electron should enter there. 4f orbital will enter. Since there is no 4f orbital here, therefore it is not a F block. It is not a lanthanide. Okay, so lanthanides, lanthanum is not included in lanthanides, but it starts from there. Followed by lanthanum are the lanthanides, therefore the name. Yes, are you getting my point? So let us move to the next point. So here we'll see how. So lanthanides, the general configuration is 4f 1 to 14, 5d01, 6s2. When we talk about the atomic size, very important concept we'll be covering here. So atomic size anta andre enu? So when we atomic size, regularly we have discussed, but D block alli we have seen about the atomic size variation. So here when we talk about the atomic size in lanthanides alli, as you progress from lanthanum to lutetium, there is decrease in the atomic size, atomic or ionic size. There is decrease in atomic and ionic sizes. Now the question is, why there is decrease in the atomic or ionic sizes? So here we talk about a term which is a very unique feature anta anbodu. That unique feature is nothing but lanthanide contraction. Lanthanide contraction. So what is this lanthanide contraction? So overall decrease in the atomic size and ionic radii from lanthanum to ruthenium is called lanthanoid contraction. Overall decrease in the atomic and ionic sizes, overall decrease in the atomic and ionic radii from lanthanum to ruthenium is called lanthanoid contraction. Now, why there is decrease in the size? Okay, pa artha aitu. Decrease in the size is lanthanoid contraction. Why there is decrease in the size? So let us have a look here. The main reason why there is decrease in the atomic size is due to poor shielding effect. Poor shielding effect of F electrons and both, or 4F electrons and because we are talking about lanthanides. Poor shielding effect of 4F electrons. Because of the poor shielding effect of 4S electrons, there is decrease in the atomic and ionic radii. So what is this shielding effect? Let us have a brief out because new shielding effect ಬಗ್ಗೆ ಕಲ್ತಿದ್ದೀವಿ. So the electron, see, shielding effect ಅಂತಂದ್ರೆ ಏನು? So this is my nucleus. The electron which is coming from outside, so it has to enter into the orbital. This nucleus will pull the electron very strongly. Therefore, the electron starts revolving around that nucleus. So here, the electron which is entering, it is entering in which orbital? It is entering in F orbital. And the F orbital property, its own property is that the shielding effect of F electrons is very poor. F electrons shielding effect hegide, which is very pure. It is something like, you just imagine shielding effect ಬಗ್ಗೆ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಬೇಕಂದ್ರೆ, I'll give you a simple example. You are in a classroom, you are sitting here is the blackboard, and here you are sitting at the last bench, let me say. So last bench ali kuttaga, you are paying attention to the teacher. There is nobody here. Just imagine there is nobody here and you are sitting here. So you will pay attention here. The teacher's attention will be grasped by, teacher will grasp your attention very clearly because there is no obstruction here or hurdles here. And then now you imagine the condition where here there are students sitting. Some students are there. So students are sitting there. Now, because of the students, students with height agirbodu, their behavior agirbodu, because of which the attention towards the board, towards the teacher gets disturbed. Haudenilla. So it gets disturbed andaga. The question is, students irodrinda disturb agate, 101% true. So they are screening you from viewing the blackboard anta anbodu. So there is disturbance. One more factor, what important here is, what type of students are there? The type of the students comes into context. So ಇಲ್ಲಿ ಕೂತಿರುವಂತ ಸ್ಟೂಡೆಂಟ್ಸ್ ತುಂಬಾ ಹೈಟ್ ಆಗಿದ್ರೆ, if they are heighted, if they are hefty enough, okay, you will have a very less view towards the blackboard anbodu. Or the other case, if the students are disturbing, if they are disturbing, what will happen? You cannot pay proper attention, your views get still disturbed. Same logic you apply here, same thing you apply here. This F orbital electrons, their own property is that they are having very less shielding effect. So shielding effect decreases. S is more, P is then P, then D, then F. Their own property says that. They don't act as good screens. Doesn't make much difference. See here, because of this, as we grow from lanthanum to ruthenium, number of electrons in the F orbital, number of electrons in F orbital, ಏನಾಗುತ್ತೆ, the number of electrons in F orbital goes on increasing. ಯಾಕೆ increase ಆಗುತ್ತೆ ಹೇಳ್ರಿ? Because atomic size is increasing, because Z is increasing. So, but the shielding effect is very poor shielding effect of F electrons. Shielding effect ಕಡಿಮೆ ಇರೋದ್ರಿಂದ the nucleus actually number of electrons increase ಆದಂಗೆ the size should go on increasing, right? But poor shielding effect of F electrons, pure shielding effect for F electrons ಇರೋದ್ರಿಂದ inner electrons ಅಷ್ಟು ಕರೆಕ್ಟ್ ಆಗಿ ಶೀಲ್ಡ್ ಮಾಡ್ತಿಲ್ಲ ಅಂತ ಹೇಳಿ, what happens, the nucleus will pull the electrons which are farther closer, it will pull the electrons. ಅದಕ್ಕೆ ಏನಾಗ್ತದೆ ಆಗತ್ತೆ, due to poor shielding of F electrons, due to poor shielding of F electrons, the nuclear charge, it will pull the electrons strongly. Therefore, atomic radii ಏನಾಗುತ್ತೆ, it goes on decrease. So there will be gradual decrease, overall decrease in the atomic and ionic radii from moving from lanthanum to ruthenium. Are you all getting? So the same thing we had discussed in D and F block elements also. Session 2 ಅಲ್ಲಿ atomic ಮತ್ತು ionic radii ಮಾತಾಡ್ತಿರ್ಬೇಕಾದ್ರೆ we had discussed about series. See, D block ಅಲ್ಲಿ there are 4 series. ಹೌದೇನಿಲ್ಲ? Series 1 ಇದೆ, series 2 ಇದೆ, series 3 ಇದೆ, series 4 ಇದೆ. Yes. So series 1, the atomic down the group atomic size ಹೆಚ್ಚಿಗೆ ಆಗ್ಬೇಕಲ್ಲ. Series 2 atomic radii is more than series 1. The atomic radii of series 2 is more, comparably more than the atomic radii of series 1. But when you see the series 3 and series 2, atomic radii of series 3 is not very much more. It is almost same compared to atomic radii of series 2. And that time also we had discussed about Lanthanoid contraction, because ಯಾಕೆ ಹೇಳಿ ನೀವು ಇದು ಥರ್ಡ್ ಸೀರೀಸ್ ಅಲ್ಲಿ ನೋಡಿದಾಗ ಹಿಯರ್ ಯು ಹ್ಯಾವ್ 57th ಎಲಿಮೆಂಟ್, ದಟ್ ಈಸ್ ಲ್ಯಾಂಥನಮ್. ಸೊ ಲ್ಯಾಂಥನಮ್ ಇದೆಯಪ್ಪ ಅಂತಂದ್ರೆ ಅಲ್ಲಿ ಎಲ್ಲ ಯಾವಿದಾವೆ 14 ಮೆಂಬರ್ಸ್ ಆಫ್ ಲ್ಯಾಂಥನೈಡ್ಸ್ ಆರ್ ದೇರ್. ಸೊ ಲ್ಯಾಂಥನೈಡ್ಸ್ ಇದಾವಪ್ಪ ಅಂತಂದ್ರೆ there is lanthanide contraction. Lanthanide contraction ಐತಪ್ಪ, poor shielding of F electrons ಆಗತ್ತೆ. Because of poor shielding of F electrons, the atomic size, atomic radii, ionic radii gradually decreases. Yes. So that's the reason, that is called lanthanide contraction. Now, what are the causes and consequences of causes we discussed? What is the consequence of this lanthanide contraction? ಏನಾಗತ್ತಪ್ಪ lanthanide contraction ಆಗೋದ್ರಿಂದ? So there is similarity in the atomic and ionic radii between 4D and 5D series. That's what we discussed. Second point is high density of post lanthanides. Post lanthanides andre enu? The elements following lanthanum, that is from 72 to 80 elements. These are called post lanthanides. Third transition series al barteo. So from 3D to 4D, from 3D to 4D series, atomic mass increases. Atomic mass increases. Excuse me. Atomic size or atomic radii also increases. But from excuse me, please. But from 4D to 5D, if you move from 4D to 5D, atomic mass is still increasing. Atomic mass increase ಆಗ್ತಾ ಇದೆ, but atomic size is same. Therefore, elements of 5D, atomic size ಏನಿದೆ? Atomic size is same. Mass increase ಆಗ್ತಿದೆ, but size is same. Therefore, elements of 5D series, they are having what? They are having high densities, almost double to those of 4D series, almost double. That is also a consequence of lanthanide contraction. Coming to the third point, that is basic character of hydroxides. Basic character of hydroxides. So hydroxides, how do we represent hydroxides of lanthanides? Lanthanide is generally represented as Ln, and hydroxide of lanthanide is LnOH thrice. Lanthanide, any hydroxide of lanthanide is represented by this formula. Metals with larger ionic radii give strongly basic hydrides. They give basic hydrides. Yes, with larger atomic radii. Along lanthanide series, ionic radii gradually decrease. So basic character ಏನಾಗುತ್ತೆ? Along lanthanides, it also goes on decreases. Basic character of lanthanides goes on decreasing. So I can say lanthanum hydroxide ಏನಿದೆಯಲ್ಲ, it is most basic. I can say this, lanthanum hydroxide is most basic. Ruthenium, the last member of lanthanides, is least basic anta anbodu. It is least basic. Getting? So here, these are the consequences of lanthanide contraction. These are the consequences of lanthanide contraction. So consequences ಅಲ್ಲಿ poor, because lanthanide contraction ಏನಾಗಿ ಯಾವ reason ಕಾಗತ್ತೆ? What is the cause of lanthanide contraction? It is the poor shielding effect of F electrons. And consequences ಬಂದ್ಬಿಟ್ಟು, what are the consequences? There is similarity in atomic, there is similarity in the radius ಅಂತೀವಿ. So 4D 5D series ಅಲ್ಲಿ similar atomic radius ಇದೆ. Then you have the second reason, high density of post lanthanides. Density ಹೆಚ್ಚಿಗೆ ಆಗುತ್ತೆ because atomic mass same ಆಗುಡುತ್ತೆ. But what is happening? Atomic size same ಆಗಿದೆ, but mass is going on increasing. Therefore, the density increases. And when we talk about basic character of the hydroxides, across, when you move from lanthanum to ruthenium, there is gradual decrease in the ionic radii. Therefore, basic character along the hydroxides also goes on decreasing. So most basic is in the beginning of the lanthanides, least basic is at the end of the lanthanides anta helbodu. Fine. So here Atomic size and at ionic radii, ionic size from left to right decreases due to increase in the nuclear charge. This is known as lanthanide contraction. This is known as lanthanide contraction. All lanthanides, they are silvery white soft metals and they tarnish rapidly in air. This is a general characteristic of lanthanides. Many trivalent lanthanide ions are colored. Okay. So to understand this, let us first try to understand something related to oxidation states. So what are the oxidation states, or what oxidation states are being shown by lanthanides? Fine. Okay, let me take the next slide. So here we are going to talk about oxidation states. Okay. So the most common oxidation state. Let me speak about first most common oxidation state. Most common oxidation state shown by lanthanides is +3. It is +3. That means all the lanthanides they form +3 ions. Ln +3 trivalent ions. But in some cases, I can say the possible oxidation states shown by lanthanides are, they are +2, +3, and +4. So +2, +3, +4 oxidation states are shown. So +3 is common oxidation state, understood. Now the question arises, +3 common state idre, why do some of the lanthanides show +2 oxidation state and why do they show +4 oxidation state? See, occasionally you may find +2 or +4 states in the solution state, solid state, solution state ali nodಬಹುದು now. Now, why sometimes +2 or +4 oxidation states come in context? Reason enu? Why? If +3 is common, why sometimes you get +2 and +4? The reason is, the answer for this reason lies in electronic configuration. It lies in the electronic configuration of those particular elements, ions and more. So what does that mean? So let us try to understand this. Because coming in the state of +2 or coming in the state of +4, they attain stability. The main reason is they attain stability. Now, you know, all the elements try to become stable. They try to attain stability by losing or by gaining electrons. And why do they attain stability? How do they attain stability? They attain stability such that they have complete filled configurations like noble gases. Athwa, we have studied in the other context also, they lose or they gain electrons to attain stability. Ali stable configuration yavag agate, when there is half filled configuration. Half filled configurations are stable, or fully filled configurations, correct? So half filled mattu fully filled configurations, they are stable. Therefore, in some cases, +2, +4 state ali yak bartappa elements so lanthanides ali, because by gaining +2 state, a solution state agirbodu, solid state agirbodu, by coming into +2 state, they become stable. Mostly half filled configuration bandbidutte no, or particular element by attaining +4 configuration, it becomes stable. It might be fully filled configuration bandbidutte no. Yes, to explain that, we have example also. You have EU plus europium +2. This is stable because if you look at the configuration of EU +2, it is 4f7. See here, 4f, 7 orbitals there, degenerate orbitals, and all are half filled. Singly filled, 7 electrons are present. So half filled configuration bandirodrinda, it becomes extra stable. Similarly with yttrium +2, this is also stable because of configuration 4f14. So 7 orbitals there, all are fully filled. All 14 electrons fully paired agate. So because extra stability is due to what? It is due to completely filled 4f orbitals. So because of this, they may attain +2 or +7 state. Now, these ions in +2 or +7, to go much in detail, +2 +4 state ali I'm sorry, +2 +2 state ali bandaga, these two examples, they act as strong reducing agents. Please mark this point. +2 state ali iddaga, the lanthanides which are in +2 state, they act as strong reducing agents. Why? See, because of the stable configuration, they have entered +2 state. stable configuration irodrinda, they have entered +2 state. But what is the common oxidation state of all the lanthanides? Common oxidation state of all the lanthanides is +3. That is their religion ಅನ್ಬೋದು, correct? So ಅವ್ರದೊಂದು ಫ್ಯಾಮಿಲಿ +3 ಅಲ್ಲಿ ಇರಬೇಕು ಅಂತ. But somehow ಏನಾಗಿದೆ, the electrons have gone to +2 state. Now they know they want to come back to their original place, their original family. So somehow from +2 it wants to come to +3. So if they want to go from +2 to +3, how they can go from +2 to +3? +2 in the +2 state agbekanದ್ರೆ it should lose one electron. It should lose one electron. So loss of electron, losing an electron antandre enu? Losing an electron antandre it is oxidation. Means it itself gets oxidized. These ions, they itself get oxidized and they will reduce others. They itself get oxidized and they will reduce others. Therefore, they are called as strong reducing agents. Getting my point? Same thing you apply here. You have an example, cerium +4. Or you take so many examples, Pr +4, you have Tb +4, you have divide, ribosmium +4. Illi, the common oxidation state is +4, but sorry, the stable oxidation state is +4, but they want to come to which state? Common oxidation state, +3 barbekappa. By +3 barbekantandre, what they have to do? They have to gain one electron. So gaining of electron andre enu? Gaining of electron andre it is reduction. That means they will help in reduction. They itself get oxidized. Yes or no? They will help in reduction. Itself get oxidized. Therefore, the lanthanides, the ions of lanthanides which are in +2 state, they act as strong reducing agents, and the ions of lanthanides which are in +4 state, they act as strong oxidizing agents. Very important concepts. Clear with this? Yes? Okay, fine. Now the general characteristics which we were seeing. The general characteristics. Yenappa general characteristics of lanthanides. What are the general characteristics? First is the appearance. As we see, lanthanides, they are silvery white soft metals. They are silvery white soft metals. Silvery white soft metals, and they tarnish rapidly in air. Because when they are exposed to air, they develop a layer coating anta anbodu. Therefore, ಏನು ಹೇಳ್ತೀವಿ ನಾವು, their silvery nature disappears and they tarnish in air. The hardness increases with increase in the hardness increases with increase in the atomic number. As the atomic number increases, the hardness goes on increasing. Particularly, there is an element in lanthanides, that is samarium. Samarium. ಹೇಗೆ ನೆನಪಿಟ್ಕೊಳ್ಳೋದಪ್ಪ? Samarium is hard steel. It is very hard. Steel hard ಅನ್ಬೋದು. It is steel hard metal. Yes, element. So samarium, samrat ಅಂತ ನೆನಪಿಟ್ಕೊಳ್ಬೋದು. Samrat ಅಂದ್ರೆ ಏನು? Raja is very strong, ಅಲ್ಲ? Is very hard. ಹಂಗೆ ನೆನಪಿಟ್ಕೊಳ್ಬೋದು. Samarium, just a memory tip, what you can say. Samarium is steel hard. It is an element of lanthanides only. Then when we talk about, they are typically they have typical metallic structure. Then they are good conductors of heat, good conductors of electricity. General characteristics of metals will hold good here. Then many trivalent melting points of this melting points of this lanthanoids, it lies between 1000 to 1200 degrees Celsius. 1200, I'm sorry, it lies between 1000 to 1200 Kelvin. 1200 Kelvin. But samarium, since it is very hard, other melting point ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ಇದೆ. The melting point of samarium is 1623 Kelvin. This is Jasti expected is between the range of 1000 to 1200, but samarium is much more higher. Melting point of samarium is much more higher. Many trivalent lanthanide ions, they are colored. And why is the color? It is because of the electrons present in the F block. Very simple. Now, D block allinu colored compounds nodidivi. Some of the lanthanide ions are also colored. The reason is the electrons in the electrons from F orbital irtakanta electrons, they'll be jumping, yes or no? So they'll be jumping from ground state to the excited state. So when they go to excited state, they say excited, and then it is not that stable. For every electron, there is a stable state. So when they take energy and go to higher state, that state is called excited state, and that is not stable. Therefore, a electron in madate, adu nanke jaga allapa, I'll come back to my place anta heli. When it jumps from excited state to its ground state, it will be emitting energy. So the energy corresponding wavelength enideyala, that is seen as a colored compound. Adu color agi baratte corresponding wavelength, and light is seen there. Therefore, we say they form colored ions anta. See, lanthanum plus 3, it is it is not colored, and lutetium plus 3 is also not colored, because in lanthanum color react because of electrons in a 4f orbital. If you see La plus 3, it is 4f0, and lutetium plus 3, it is 4f14. So illy, since there are no electrons in f orbital, and here they are completely filled, therefore what you can say, there is, they do not show any color, they do not exhibit any color anta helbodu. Okay, so what is the, let us see the next property of lanthanides. So here, many trivalent lanthanide ions are colored both in solid state and in aqueous solutions. Neither La plus 3 nor Lu plus 3 ion shows any color, but the rest do so. Lanthanides are very reactive metals, just like alkaline earth metals. So reactive. They exhibit certain chemical reactions. So they show certain chemical reactivity. So what are those chemical reactivities? Now we'll see one by one. So chemical reactivities only. Lanthanides, they are having very low SRP values. SRP values and standard reduction potential values. The values range between -2.2 to -2.4 volts. Except europium, it is -2.0. Okay. So this lanthanum, any element of lanthanum, when it is burnt in oxygen, you burn in oxygen, it forms an oxide of formula Ln2O3 when it is burnt in oxygen. The second reaction is lanthanide, when it is heated with the sulfur, it forms lanthanide sulfide. Okay. When it is heated with nitrogen, it forms lanthanide nitride. When it is treated with carbon at 2500 degrees Celsius, it forms LnC2. With water, with H2O, it forms hydroxide, LnOH twice. Plus, there is liberation of hydrogen gas. With halogens are usually represented as X. It forms LnX3, halides. With acids, typically hydrogen gas is released. H2 gas is released. H2 gas is being released. So this is the chemical reactivity of lanthanides in general. So what are the uses, applications of these lanthanides? These lanthanides, they are used in the form of alloy, like you have mish metal. Mish metal is nothing but, it is a lanthanide metal, 95% lanthanide metal, and a mixture of iron, nearly around 5% anta anbodu. Yes, and traces of carbon, silicon, sulfur, calcium, and aluminum are there. This is the, what you can say, composition of mish metal. 95% tin is there, 95% is lanthanum. Okay. Magnesium mixed with 3% mish metal, it is used for making jet engine parts. It is used for making jet engine parts. Oxides are used in industries. And as you see, some of the lanthanide ions, because of a strong reducing nature, you can use them as reducing agents. You can use them as oxidizing agents. Individual oxides of lanthanides are used as phosphors in television screens and fluorescent screening also. So these are some of the applications of lanthanides. So you can see here the reactions are given. Mish metals contain about 90 to 95% of lanthanide, then 4.5% of iron, and traces of calcium, carbon, silicon. Used in cigarettes and gas lighter toys, tank and trace bullets. Coming to the next one, that is actinides. So actinides next series, second series of F block elements anbodu, athwa 5F series of F block elements are called actinides. Yes, so here you can see here the actinides are series of 14. It's actually 14. actinium ಅಂತ consider ಮಾಡಿ 15 ಅಂತ ಬರಿಬಹುದು. By 15 metal elements, it is 14 only. Please make this point very clear. This is 14 elements followed by actinium. Followed by actinium ಅಂತ ಅನ್ಬೋದು. I have told you also why followed by actinium. Actinium ಅಲ್ಲಿ ಮನೆಯಲ್ಲಿ you 14 actinides ಇದೆ. They are called actinoids. Yes, the atomic numbers, they start from 89 is actinium, so 90 to 103. This becomes 14. Actinium na follow ಮಾಡಿ ಅಂತ ಹೇಳಿದ್ದಕ್ಕೆ we say 15 also sometimes. Okay, don't get confused. Total F block elements are 14 plus 14, that is 28 elements are there. Fine. Okay, the general electronic configuration banbittu, you can write noble gas configuration. Here you have 5F 0 to 14, then 60 0 to 2, and then 7s2. So this is the general configuration of actinides. Then these are radioactive elements, as we just now discussed. So radioactive, it's a phenomena, not a process. Process andre which happens regularly. Phenomena andre it is important in its own way. Okay, so radioactive elements, they exhibit, they give out radiations on their own. Fine. Naturally occurring actinides are thorium, protoactinium, uranium. The first three elements in the, they are naturally occurring elements. And uranium, these are naturally occurring. They have relatively long half-lives. Radioactivity and takshana we come into context half-life. Half-life andre eno, at that particular time, half of the concentration of that particular element has disintegrated. ಅದು ಕಳೆದು ಹೋಗಿದೆ. ಹಾಫ್ ಆಫ್ ದ ಅದು ಕಾನ್ಸಂಟ್ರೇಷನ್ ಆಫ್ ದಟ್ ಪರ್ಟಿಕ್ಯುಲರ್ ಎಲಿಮೆಂಟ್ ಹ್ಯಾಸ್ ಡಿಸಿಂಟಿಗ್ರೇಟೆಡ್. ಅದಕ್ಕೆ ಹಾಫ್ ಲೈಫ್ ಅಂತೀವಿ. ಸೊ ದ ಬಿಗಿನಿಂಗ್ ಆಫ್ ದ ಸೀರೀಸ್ ಅಲ್ಲಿ ಬರುವಂತ ಎಲಿಮೆಂಟ್ಸ್ ಏನಿದಾವಲ್ಲ, ದೇ ಹ್ಯಾವ್ ರಿಲೇಟಿವ್ಲಿ ಲಾಂಗ್ ಹಾಫ್ ಲೈಫ್ಸ್. ಆನ್ ದ ಅದರ್ ಹ್ಯಾಂಡ್, ಇಫ್ ಯು ಸಿ ದ ನೆಕ್ಸ್ಟ್ ಎಲಿಮೆಂಟ್ಸ್, lateral elements in barattala, followed by uranium, they are called transuranic elements anti no. Elements which come after uranium, they are called transuranic elements. These transuranic elements enidavala, the transuranic elements yavavappa, like for you have neptunium, plutonium, yes, then you have americium, then you have curium. These all elements, they are called up to last yavadappa, the last element, lawrencium. These are all called as transuranic elements. Okay, they are not naturally occurring. They are man-made. These elements are man-made and are obtained by nuclear transmissions. Okay, when you see the atomic and ionic radii of actinides also, like how you have lanthanoid contraction, similarly in actinides also there is something called actinoid contraction. Things are simple here because all we have studied, all the things are same as we have studied in case of actinides. So actinoid contraction inapa, as you move from thorium to lawrencium, atomic radii gradually decreases, and this decrease is called actinoid contraction. What is the reason? The reason is poor shielding effect of F4F electrons. Okay, only difference is in case of lanthanides you have 4F electrons, in case of actinides you have 5F electrons. That is the only difference. Okay, fine. So here actinides alli nodidre what again we come into context, that is most of the ions are colored. The reason is what? The reason is same again, because 4F electrons jasti ive, they will be jumping from one state to another state. So ground state in the excited state will jump adaga, they are not stable there, they try to come back to normal state. Normal state alli barbekadre they have to give that extra energy what they have taken. So when they are giving that extra energy transmit agirattala, that transmitted energy corresponding wavelength is seen as light. So therefore they are colored. And here you can see some of the colors also. Uranium +3 is red color, +4 is green color. Then here you have +2 is yellow color. Okay, so this is about the general properties of actinides and lanthanides. So here oxidation states, when you see the oxidation states of lanthanides, they show great range of oxidation states. They exhibit a very great range of oxidation states. And great range, you have +2 oxidation state, plus 3 oxidation state, plus 4 oxidation state, plus 6 oxidation state, up to plus 7 oxidation states are being shown. The highest 5f orbitals, yake different oxidation state, variable oxidation states yavag barattappa when there is not much difference between the energy levels of the orbitals. So degeneracy iddaga not much difference, comparable energies iddaga, energy levels, so the electrons, some electrons can be lost from n minus 1 to n minus 2 electrons loss ಆಗಬಹುದು, ಆವಾಗ ವೇರಿಯಬಲ್ ಆಕ್ಸಿಡೇಷನ್ ಸ್ಟೇಟ್ ಬರುತ್ತೆ. ಸೊ 5f orbital electrons, they also participate in bonding. So first half series exhibit highest oxidation states. The highest oxidation state shown by lanthanides is +7, and that is being shown by neptunium and plutonium. The tendency to show oxidation states, the tendency to exhibit oxidation state increases from thorium to plutonium, up to plutonium. So thorium +4 is there, H shows +4. Then you have A, protactinium shows +5. Uranium can show +6 also. Then after plutonium, the tendency to exhibit higher oxidation states goes on decreasing. That is from berkelium. Berkelium onwards, only +3 oxidation state is possible. Okay, only +3 oxidation state is possible. So here, if you see the lower oxidation states, when you see the lower oxidation states, in lower oxidation states, the compounds are ionic. Lower oxidation states, compounds are ionic. But in higher oxidation states, the compounds are covalent. Please do remember this point. Lower oxidation state, compounds they will be ionic in nature. When they come to higher oxidation state, the compounds become covalent. Fine. Okay. So this is about the property. Actinides exhibit a range of properties. Actinides exhibit a range of oxidation states due to comparable energies of 5d, 5f, 6d, and 7s orbitals. The general oxidation state shown by actinides is +3. Again, same like lanthanides, actinides also show +3 oxidation state. Actinides. All the actinides are strong reducing agents and very reactive. They are strong reducing agents and very reactive. Before that, appearance nodidre, they are also silvery. They are also silvery white metals. Silvery white metals. Their cations are colored both in crystalline as well as in solution state. They are colored. Okay. The color is due to again what? The color is again due to FF transitions. We have already discussed this point. Okay. Then readily lose electrons. Since they readily lose electrons, they lose electrons very easily. Therefore, they act as strong oxidizing agents. They are having very high melting and boiling points. These lanthanides, they have very high melting and boiling points. Their melting points and boiling points are high because they are metals, hard. Metals hard irodrinda, they have very high melting and boiling points. Okay. They are strongly paramagnetic in nature. They are strongly paramagnetic in nature. Why they are strongly paramagnetic in nature? Because they are having unpaired electrons. See, magnetic property is shown by the presence of unpaired electrons. So actinides are paramagnetic and they have got unpaired electrons. But if you see AC +3 actinium, that then thorium +4, uranium +6, these are diamagnetic, and even lawrencium +3 is also diamagnetic. Why these are diamagnetic? The reasons. Because of absence of unpaired electrons. Because if you see the configuration of these three, it will be 5f0. Here the configuration is 514. Either it is no unpaired electrons, or it is completely filled. Completely filled irodrinda, there is no unpaired electrons. So because of this, these particular ions are diamagnetic. Otherwise, the ions of actinides are paramagnetic. These actinides, they have high tendency for complex formation also, compared to lanthanides, because of higher charge and smaller ionic size. Lanthanides compare madidre, they have high charge and a small size. Adakke they form good complex compounds anta anbodu. These actinides also form chelates with organic compounds. Like for example, you have example of EDTA, ethylene diamine tetraesteric acid, and oxime. So these are the examples where chelate formation, chelates we discuss in coordination compounds. Coming to chemical reactivity, highly reactive, especially in finely divided state. Finely divided state, they are very reactive. Boiling water gives mixtures of, along with boiling water, gives a mixture of oxide and hydride. Combined with most nonmetals at moderate temperatures, readily attacked by HCl. Okay, then they are not affected by alkalis. So these are some of the properties of chemical properties of lanthanides and actinides and both. So when we compare, when we talk about lanthanides and actinides together, we have something here. So you can see here lanthanides. So lanthanides are chemical elements found in the periodic table. F block are of the lanthanide series. Actinides are chemical elements found in actinide series of F block. So range 50 to 71, here 89 to 103. Here actually it is 58 to 71 for 14 elements, 57 is lanthanum, 89 is actinium, 90 to 103. They are from 6th period and belong to 3rd transition series, making up first inner transition. Okay, one more point here. F block elements are called inner transition elements. Yake inner transition? Transition is n-1th shell. Inner transition yake? Because n-2th shell. They are present within the transition elements. Correct? Therefore, they are called inner transition elements. And these form 7th period and belong to 4th transition series. Series 3, series 4. Fine. Their valence electrons are present in 4f orbital and here they are present in 5f orbital. The binding energy of 4f orbitals is greater. Here the binding energy is quite less. Because atomic size ಸ್ವಲ್ಪ ಜಾಸ್ತಿ only few cases besides +3 oxidation state, they also show common oxidation state of all lanthanides is +3. But here they also exhibit +2 and +4 and we have seen also. They have higher oxidation states from +4, +5, +6, +7, neptunium, +7 is there. Besides common oxidation state yavdu +3. Mostly their ions are colored and here their most ions are colored. Colored ions is there. FF transition goskara because the reason is FF transition. Their tendency to form complex ions is less and here the tendency to form complex ions is more. Why? Because of high charge and smaller ionic size. Their compounds are less basic than actinides. They have more basic compounds than actinides. Lanthanides are non-radioactive except for promethium. Promethium is an element of lanthanide and it is quite radioactive, but except promethium, all lanthanides are non-radioactive. All are radioactive. Naturally radioactive yavavappa thorium, plutonium, protactinium and uranium. After uranium, transuranic elements in barattala, they are what you can say transuranic elements. They are not naturally occurring, they are artificially made, and all the lanthanides, they are having a very small half-life. Yes, to small appa. See, half-life period, this point also I just missed out to tell you. Radioactivity andaga half-life bande barutte. Half-life period of these transition starting ಅಲ್ಲಿ ಇರತಕ್ಕಂತ thorium, protactinium, then uranium half-life is quite up to a day vargu ide. They have half-life relatively long half-lives, but the latter ones they have post transuranic elements antivalla, they are having a very small half-life. Eshtappa? From 1 day to 3 minutes. From 1 day to 3 minutes. Imagine 3 minutes ಅಲ್ಲಿ half concentration. ಏನದರ ಅರ್ಥ? The half life of what example you can take very specifically ನಿಮಗೆ ಹೇಳ್ಬೇಕಪ್ಪ ಅಂತಂದ್ರೆ lawrencium, the half life of lawrencium is just 3 minutes. What does that mean? Half of the lawrencium, half the concentration of the lawrencium is already disintegrated in 3 minutes. 3 minutes ಅಲ್ಲಿ disintegrate ಆಗುತ್ತೆ. So you think element whose half-life is so less, can we produce them in more quantity? More quantity ಅಲ್ಲಿ produce ಮಾಡಿದ್ವಪ್ಪ. Can we produce them in kgs? See, you produce it in kgs. Within 3 minutes, half of its concentration gets disintegrated. Can we produce them in more quantity? No, not possible. So by the time you produce that, it has already disintegrated. Half of it is disintegrated, right? Similarly, can you study such elements in detail? Properties of such elements can be studied in detail? Not really, right? Because to study, you need more time at least. Pratyondu property study ಮಾಡಬೇಕಂದ್ರೆ we need sufficient amount of time. In 3 minutes, you study one property at least. That is not possible. Therefore, that's the reason study of many elements of actinides has not become that easy, that possibly. So here you can say good news is that we will have we'll have to study less for actinides and anbodu, right? So jokes apart, this is about the half-life periods of the lanthanides and the about the lanthanides. Uranium ಆಗಿರಬಹುದು, naturally occurring radioactive elements after uranium ಆಗಿರಬಹುದು. Yes, so this is about the actinides. Now, general applications of all D and F block elements. So iron and its amalgam. Amalgam anta andre enu? When we talk about amalgam, that means it is an alloy which compulsorily contains mercury. So an alloy with mercury is called amalgam. So iron and its amalgam and steel are utilized broadly in the development industries. Titanium is as a part of manufacture of airship and space processes. Tungsten comes in use in making electrical fibers. Tungsten, yake electrical fibers? Because high melting point is there, yes or no? Manganese dioxide comes in use as a part of dry battery cells. Zinc comes in use as a negative anode to fix batteries. Niobium composition are perfect parts to fly motors. See, these are the applications. Tantalum comes into use to make expository baits. It is used as a part of photography. This you have studied in basics. 10th ಅಲ್ಲಿ ಕೂಡ ಕಲ್ತಿದ್ರಿ. Silver bromide AgBr. It will reaction photography, part of photography. ಯಾವ photography? Black and white photography ಅಲ್ಲಿ ಯೂಸ್ ಆಗುತ್ತೆ. ಹೇಗಪ್ಪ? See, AgBr, when it is exposed to sunlight, it dissociates to give you Ag plus Br, bromine is given out. So this, because of this layer of blackish or grayish layer is being developed. So there you use it as black and white photography anta anbodu. So many D block elements of transition, many D block elements are transition metals and their compounds find their use as impetuses in chemical reactions. We see they are used as catalysts in chemical reactions. Palladium chloride comes into use in Becker's process for conversion of ethane to ethanol. Iron comes in use for manufacture. We have discussed about the applications of D block elements. Just I'm recalling that. Haber's process ali, manufacture of we use iron. Ziegler-Natta. What is Ziegler-Natta catalyst? A complex of trimethyl aluminum and titanium tetrachloride comes into the use in polymerization of ethene to polythene. Uses of F block: lanthanide alloys, mesh metal utilized for creation of instrument steels and heat resistances. Carbides, borides, nitrides. We have seen lanthanum carbides, lanthanum borides, lanthanum nitrides are being prepared using carbon, boron, and nitrogen. Of lanthanides, they come in use as refractories. Lanthanide oxide comes in use as cleaning glass abrasives. So this is all about lanthanides and actinides. Hope all the concepts are quite clear. I have been justice to all the concepts, which will help you to solve the numericals. Thank you for this class. Thank you again.